All right, so our goal is to understand vision. How does your eye focus an object onto the retina? Okay, so in preparation for that, we'll study some of the physics that is involved. Okay. By the way, so Thomas Edison, who was considered one of the greatest inventors, had this to say: "I have not failed. I have found 10,000 ways that don't work." Okay, so this was when he was inventing the light bulb. Okay, one of the things. Okay, so geometric optics is the study of phenomena where light travels in a straight line. Okay, so here's sunlight reaching your eye directly. In fact, you're hardwired in your brain to think that light travels in a straight line. Okay, so and we'll see the effect of that. So here's light that is reflected off a lake. Okay, so the rules of geometric optics are relatively simple. Okay, so we'll talk about that. So here's a beam of light that is incident on a glass medium. Okay, it starts in air and you see that this light bent. This beam didn't travel straight in a straight line. Okay, so when a beam of light travels from one medium to another medium, it will bend, and this is called refraction. It will bend if its speed changes in this new medium. If the speed in the new medium were the same, then it would travel in a straight line. Okay, so if the speed doesn't change, it won't bend. So any wave, when it bends, it's bending because its speed changes. Okay. When light changes direction while passing from one medium to another, it is said to have been refracted. Okay. Light changes directions when it goes from medium to another because its velocity changes. Okay. Now, so here's the deal. If it slows down in this medium, then it will bend towards the normal. This is called the normal. The normal is the perpendicular to the two interfaces, to the interface. And if it slows down, then it'll bend towards the normal. And if it's going faster in this medium, it will bend away from the normal. Okay. So for instance, we can do this air and glass. So there's the normal. And a beam of light. Okay. In air, it's traveling faster. In glass, it travels slower. So it'll bend towards the normal. And if you did the opposite, if it started from glass, since it was in air, it's traveling slower, it'll bend away from the normal. Okay? So this is called refraction. The bending of light when it travels from one medium to another, its change in direction is called refraction. Okay, if you have a smooth surface, light will be reflected. This is called the angle of incidence. So there is a mirror, there is the normal. Normal is perpendicular, and that's called the angle of incidence. This is called the angle of reflection. This angle is equal to that angle. So that's how light reflects. Now, if the smooth surface is rough, then light gets scattered. Okay, so what does this mean? So for instance, if you have a still water, a smooth lake, you can see a reflection. And if on the same lake, if you have rain falling, you have specular reflection. Now you won't be able to see your image anymore. Okay. All right, so okay. Retroreflection. Okay, so retroreflection is the following phenomenon. So if you have two mirrors like this that are perpendicular to each other, you send a beam of light like that, it'll reflect, and you see here is the reflected beam that is coming parallel to the incident light. Okay. Now, if you have three mirrors that are perpendicular to each other, okay, so for this thing, you have to be careful with the angle of incidence. If you have 3 mirrors that are perpendicular, you can hit it anywhere and that beam will come right back at you. Okay, so if that corner, so here's the deal. If those corners were mirrors, I can hit this with a laser and that laser would come right back at me. That's a retroreflector. Okay. Well, what you ask, what use is that? Okay, so we have mirrors like that on the moon. When we went to the moon, we placed mirrors like that, and we shoot lasers at the mirror, and the laser comes right back at us. And we can measure the distance to the moon to that accuracy. You use these things all the time. So here, this is also a retroreflector, a little plastic spherical bead. You send light like that, and it comes right back at you. You hit this beam in any place, and it'll come right back at you. And we use these in stop signs. So there's little beads in that paint, and your headlight hitting that sign comes right back at you. That's how you see all those signs at night. You know, you ever wonder, there's a stop sign over there, and you can see it. Yeah, so that's your light from your headlight coming right back at you. These little things are retroreflectors in your tail light. Okay, so even if somebody driving in front of you, they don't have their lights on, your headlight will be reflected back. And so those are retroreflectors. Here's that mirror on the moon that I talked about. So those are retroreflectors. Okay, so we said that, so again, this is glass and this is air. So there's the normal, and a light beam entering from air bends in glass. Okay. Now the amount of bending will depend on how slow the light is moving in this medium. The slower it is moving, the more it will bend. Okay? And that is measured by something called the refractive index of the material. Okay? So this is the speed of light in vacuum. This is the speed of light in the medium. The slower it is moving in the medium, the higher the refractive index. Okay? And if you wear glasses, you go to an optometrist and you buy a high refractive index lens. It's more expensive, and that's because it's a thinner lens. You don't need as much material to bend the light. Okay? So the refractive index, slower the light travels in that medium, higher the refractive index. Okay? Higher the refractive index, more bending that can be done. Okay? So higher the refractive index of the material, more the light rays will bend. So, these are the common refractive indices that you find at an optometrist, 1.4 to 1.67. Okay. And that's the most expensive lens. Okay. Okay, again, refraction is it's changing direction. When a ray enters a medium where it's traveling slower, the ray bends towards the normal. Okay, and when it's traveling faster in the medium, it will bend away from the normal. Okay. There's a formula that relates the two angles, and this is given by Snell's law. And Snell's law says N1 is the refractive index of medium 1, N2 is the refractive index of medium 2. Okay. N1 times sine theta 1 is equal to N2 times sine theta 2. Okay. So that's just a formula that relates the the two angles. This is called the angle of incidence. This is called the angle of refraction. Okay. Paths of all rays are reversible. What that means is if you shoot a beam like that and it travels like this, if you shoot a beam in this direction, it'll travel back in that direction, exact same direction. Okay. So all light paths are reversible. Okay, here's a convex lens. It's also called a converging lens, and it's called a converging lens because if you shoot a beam of parallel light rays, it converges to this point, and this is called the focal point. Every lens has two focal points, one on the right and one on the left, and this is called the focal length. Okay. And for a given lens, the focal lengths are the same. The right side and the left side focal lengths are the same. Anyway, this is called a converging lens. Okay. 1 over the focal length is called the strength of the lens, is the strength of the lens. Okay. So shorter the focal length, greater the strength of the lens. Okay. And if you measure the focal length in meters, the strength comes out in diopters. And that's what an optometrist uses, a diopter. Okay? So the strength of the lens is defined as the inverse of the focal length and measured in diopters. Okay. So, for instance, your cornea and your lens together form a lens, and the cornea shape doesn't change, but the lens in your eye can change its focal length. So the combined strength, so when you're looking at far off objects, the combined strength is 50 diopters. And when you look at close by object, then the strength has to increase, and it can rise up to 54 diopters. Okay. So if for your vision, your strength changes from 50 to 54 diopters. And it is the strength of the lens that is changing. Okay. So when I look at that, see, so here's your eye is pretty amazing. See, the strength of this lens cannot be changed. But, okay, no, my eyes are bad, but anyway, good eye, you can look at infinity, an object very far away, and your strength is 50 diopters, and then within a second, you'll start reading something, and your lens power, your eye strength changes to 54 diopters, just like that. Okay, so your eye is pretty amazing. We'll come to that next week. Okay, a concave lens or a diverging lens. Okay, it's also known as a diverging lens. You shine a beam of parallel light, and it diverges like this. Okay, this is used for distance eye correction. Okay, so for myopic, if you can't see distant objects, this is the kind of lens that is used. Okay, so let me show you this stuff. All right, so how that works. All right, so for instance, my power is about 5 diopters. Okay, that means I can't see anything beyond this point. Okay, so what is this thing doing? See, I can't see anything beyond this point. So how do I see her? Okay, what this lens has to do is make an image of her within this point. This is my far point. Okay, so if I want to see anything that's far off, its image has to be made within my far point. Do you guys understand that? All right, so here's this lens. Okay, here's this object. And so there is the focal length of this image. See, no matter where the object is, the image is within my far point. So when I went to the doctor, they find out what my far point is, okay, and that's the focal length they give you. Any image is made within my far point. Okay? So that's what happens. So again, you see, no matter where I move this lens, a concave lens, is used for distance vision. Okay? So, so if you're here, you can find your far point like this. By the way, the focal length of this guy is negative. We'll come to all of that. So if your power is -2, what that means is your far point is 50 centimeters away. Okay? -2 is 50 centimeters is half a meter. 1 over 0.5 is 2 diopters. Okay, so if your lens power is let's say one diopter, that means your far point is 1 meter away. Okay, so that is the far point. Okay, so you're using a concave lens. Where did my thing go? Okay, so this is a concave lens. You're using a concave lens for to correct nearsightedness. Okay, so people with this problem need glasses to see clear objects that are far away. We'll talk about real and virtual images. Okay, so now let me go back to that for a second. Okay, so here are, okay, now what this diagram shows you is the following. These are called principal rays. What I'm going to show you is what a ray will do. So here's your object, a ray going like this, parallel to the principal axis. The principal axis is that dotted line. Okay, the dotted line goes through the center of the lens. Okay, a ray going parallel to the principal axis will go through the focal point. So these are called principal rays. We use this for image construction. A ray going through the center of the lens will go straight through. It's not deflected. A ray going through this focal point will come out parallel to the principal axis. Okay, so what this is now we've shown you the behavior of 3 rays going through the lens and what they'll do. So if you remember these 3 rays, the properties of these 3 rays, you can construct any image. So again, a ray going parallel to the principal axis will come through the other focal point. A ray going through the center of the lens will go undeflected. A ray going through this focal point will come out parallel. Okay? Similarly, here are the principal rays for this guy. For a converging lens, a ray going parallel will emerge like that. It'll appear to come through the focal point. A ray going through the middle of the lens goes undeflected. Okay? And a ray that would have hit that focal point will emerge parallel to the principal axis. Okay, so those are the principal rays. All right, and so that is what's used to construct images. So here's an object for a converging lens. That's where the image is formed. If actual rays meet at the image point, this is called a real image. To see this, you have to project it on a screen. Okay, so this is what happens in a movie theater. Okay, so this is the real image. So in a movie theater, the projector has a converging lens like this. This is the film. I mean, in the old days, this used to be the film, and that was the image. And you can see the image is upside down. So the film had to be upside down to project a right side up image. Here's a converging lens. If the object is within the focal point, then it forms a virtual image. So these rays come out like that, and if you're standing there, if you're looking at these rays, remember your brain is hardwired to think light travels in a straight line. So your brain thinks this ray is coming from there, this ray is coming from there, these rays are meeting there. And that's where it constructs an image.
You're using your finger to point,
Uh-huh.
not the pointer itself, so
Oh.
you can't see what you're pointing at on the
All right. Okay.
talking about which
Okay.
one.
Okay, so this ray comes out like that, this ray comes out like this ray. If you're standing here and watching these rays, Your brain is hardwired to think that light travels in straight lines, so your brain constructs an image over there. Pretty amazing. Okay, so here's the object, and that's where the image is. And you can see that this is a magnified image, and this is what happens when you use a magnifier. You guys have used a magnifier? And so if you are reading small print, that small print has to be within the focal length of the magnifier, okay? And then you get a larger image. This is how microscopes work. Microscopes essentially use two of these lenses. Okay. Yeah. All right, so those are the three principal rays. Okay. And you can use these three principal rays to form the image of this guy over there. Okay. Okay, so here's a concave lens. Okay. And this ray will diverge, and it'll appear to diverge from this focal length. A ray going through the center goes undeflected, and a ray that was directed at the other focal point will emerge parallel to the ray. Okay. Concave lenses always form virtual images. So this is the lens that I have, and that's my far point. Every object, its image is formed. It's a virtual image formed in front of my far point. Okay. So this is a simple magnifier. Okay. This is a convex lens. There is the focal point. If the object is placed within the focal point, this ray goes out like that, and this ray going through the center goes straight through. If you're looking at these images, at these rays, again, your brain thinks these rays are coming from that point, and that's where the image is formed. Okay? And okay. So this is called a virtual image because actual rays are not intersecting at that image point. Here's how mirrors form images. So here's a plane mirror. A light ray coming from here reflected like that. That ray reflects like this. And if you're looking at these rays, they will appear to come from there. And that's the virtual image. Okay. A plane mirror, the image size is the same as the object size, and it's equidistant. This distance is equal to that distance. Okay. There's just a right-left flip. So you look at your left hand, and the image will appear to be your right hand. Here's a concave mirror. Okay. And this is a magnifier. You guys use. You might have them in your bathrooms. So this is your magnifier. This is a convex mirror. This is what's on those aisles in supermarkets and grocery stores and stuff like that. Okay? And this is what's on your side view mirror as well in your car. Okay? The image is always virtual. It's upright. It's smaller. Okay? The only problem is it's hard to judge the distance from the image size. Okay? It's hard to judge the distance of the object. Flat mirrors are often used to make small rooms look bigger. Okay? So plane mirrors are always, if you want to make a room look bigger. All right, so here's a concave mirror. Again, if you shine light, a beam of parallel light, the reflected beams will go through a focal point. This is the kind of mirrors that are used in telescopes these days, large telescope. You get starlight like that, and that's where the image of the star would be formed, okay, near the focal point. The focal length, if this was a spherical mirror made out of a sphere, the focal length is half the radius of the sphere. Okay. All right, so here are some images formed. So here's a concave mirror, here's an object. This ray got reflected through the focal point. A ray that would go through the center gets reflected straight back. And here are two rays, reflected rays intersecting, and that's where the image is formed. This is a real image because actual rays are intersecting at that point. And to see that image, you actually have to have a screen there. You have to place a screen there. Here's a virtual image, the same concave mirror. There's the object. This light ray got reflected like that. A light ray that would go through the center gets reflected straight back, and that's where the image is formed. And that's a virtual image. So you can take a spoon or a spherical, you can take a spoon, and if you put your face close enough, you'll see a magnified image of yourself. Okay. But also this is, I mean, most people have a concave mirror in their bathrooms, and you can see a virtual magnified image. Here's a convex lens, which is forming an image there. That's a real image because actual rays are meeting there. Here's the object. These are the rays. This is a virtual image because light rays appear to come from there. Again, this is the convex mirror. It's a virtual image. Here's the object. This is the side view mirror. Mirror on the aisles in supermarkets is this kind of mirror. This object, this ray reflects like that. This ray that would have gone through the center is reflected straight back, and they appear to come from there. That's the virtual image. Okay. Okay, here's the important formula. Okay. What this formula gives you is it works for mirrors and lenses. What this gives you is this P is the object distance, the distance of the object from the mirror or the lens. Q is the image distance. Okay. And so P is this distance, so and Q would be image distance. Okay. So let me write it down. P is object distance. Q is image distance. Okay, so this formula relates object distance, image distance, and the focal length of the lens or the mirror. Okay, and it's an inverse relationship. So the formula is valid for thin lenses and mirrors. Okay, here's a sign convention. These guys can, image distances can be positive or negative. Sometimes object distances are negative. That's when you use multiple. So when you have multiple lenses or things like that in an instrument. So, but we won't use that situation too much. Focal lengths can be positive or negative. Okay, so most of the times we'll consider situations when image distance and focal lengths are positive and negative. Okay. Q is positive if the image is on the same side as the outgoing rays. Okay, so image distance is positive if the outgoing rays and the image are on the same side. Okay. So here's a situation. So here are the outgoing rays and the image is on the opposite side. And Q will be negative there. So Q is negative generally for virtual images. Okay. And again, you won't have to worry about all of that. You just need to be aware that Q can be positive or negative. And these rules tell you that, tell you when it'll be positive and when it'll be negative. Okay. So Q is positive if the image is on the same side as the outgoing rays, negative otherwise. You want to be aware of this term magnification. Okay. Magnification is image height divided by object height. Of course, in a microscope, you have magnification of 200, so that means the image is 200 times larger than the object. Okay, and that's the point of the microscope. So magnification is image size divided by object size. Okay. So here's a microscope. Okay. So it's using two convex lenses. Okay. So here's the slide that is placed behind the objective. The objective lens makes an image of the slide over here, and you see this image is inside the focal length of the eyepiece, and that will form an enlarged virtual image. Okay, so a microscope is using two lenses. So this magnifies the image slightly, and then this lens magnifies the image quite a bit. Okay. So that's a microscope. Again, that's a compound microscope. Okay, so yeah. So a simple compound microscope consisting of two lenses. Okay, so so devices such as microscopes, telescopes, cameras, and movie projectors are multiple element systems. Okay. They have multiple lenses. Okay, so we'll come to an important formula. Or the overall magnification is the product of the magnification of individual lenses. So the magnification of this instrument is the magnification of this lens times the magnification of that lens. You know. So the simplest compound microscope is constructed from two thin convex lenses. You know. This is the objective, and that's the eyepiece. Okay. All right, so this shows you the following. The object is placed past the focal length of the objective lens, and the image it forms is within the focal length of this guy, and then this image gets magnified. Okay, so the image produced by the objective becomes the object for the eyepiece. The image produced by the objective becomes the object for the eyepiece. Okay. The eyepiece is positioned so that the image produced by the objective is within the focal length of the eyepiece. Okay. It's within the focal length of the eyepiece. And then the eyepiece acts as a simple magnifier, producing a greatly magnified virtual image. So this was the image produced by this guy, and this became an object for this guy, and that's the final image. Okay. All right, so we need to know this formula. If you have two thin lenses and they're close to each other, the combined focal length, they'll act like a single lens, and the combined focal length is just, so the inverse of the combined focal length is just the inverse of the two. Okay. So this is what happens in your eye. Your cornea does most of the bending. Your cornea does 75% of the bending. Your lens only does 25% of the bending. But of course, the lens can change its focal length. The cornea cannot change its focal length. Okay. And now you can understand the following thing. When you do corrective eye surgery, what they do is they reshape the cornea, because that's doing the 75% of the bending. And, okay. So, and when you do, what is that surgery called? I'm sorry? LASIK surgery. What you're doing is you're ablating cells from the inner surface of the cornea. Okay. Most of the time what they do is they cut the cornea, flip it over, and then ablate cells from the inner surface. Okay. So since the cornea is doing 75% of the bending, that's where you need to do the correction. Okay. All right, so what this formula tells you is the effective focal length of the two lenses is just the okay, so this is the strength of this lens. The strength is the strength of this lens plus the strength of that lens. So the effective strength is the sum of these two. All right. Oftentimes you'll have lenses like this. This lens can be thought of as the sum of two lenses, a convex. Okay. So let me try and draw. Okay, so that one lens is this lens plus that lens, and that's what's shown here. Okay. And so this lens is that lens plus this lens. Okay. So for instance, when you wear contact lenses, okay, you for distance vision, okay, when I can't see far off objects, what I need is a concave lens, a lens like this, okay, and so what your contact lenses are shaped like this, so they can sit on your cornea like that, but this is this times this plus that, and this has a higher power than this, so effectively this is acting like a lens like this. So this is acting like a lens like that. Okay. So that's what this shows you. Okay. So this total internal reflection. This is the reason why internet is so cheap. This is so here's glass and this is air. If you shine a beam of light, it goes straight through. If you shine a beam of light like that, it hits like that. If you shine a beam of light at an angle greater than a critical angle, it is totally reflected. This beam is 100% reflected. Okay, what this means is, if you take a glass fiber and you send a beam like this is totally reflected, 100% reflection. So a signal, you can have a glass fiber 100 miles long, I'm just exaggerating, and you get a complete full signal out there. And this is a fiber optic cable. Okay. So you're sending a light beam without any loss, and you can pack information on this light beam. Okay. And there are techniques for doing this. Okay. And so that's why internet is so cheap. So the fiber optic cables, you can send a lot of information on there. Okay. And here's an illustration of this. See, here's a fiber optic cable. There's this letter, and you can read that letter. Okay. So physicians use fiber optic devices to examine internal organs. So when they send that tube down, it has a light source and a fiber optic cable, so where you can see the internal organs. Okay. All right. I'm sorry we had to go through it.